Hello, everyone. Welcome to another Q&A about history of science and technology. And I see a whole bunch of questions saved up here. Let's see, there's one from Robot. How far back does the idea of discrete space go, and who first took it seriously as a scientific possibility? Well, let's see. So, in antiquity, there was a lot of debate of, is the world discrete or continuous? So, the atomists, Democritus being, I think, sort of an early one, Epicurus later, Lucretius later than that, these were all in the kind of, the world is discrete. And they had the very good idea that everything in the world, with all the diversity we see, might be the result of different combinations of some small number of atoms, just combined in different ways and a few different kinds of atoms. I think Lucretius, first century AD, made the analogy, perhaps the world is put together out of atoms in the same kind of way that sentences are put together out of words, according to the fixed laws of grammar. And that was, I thought, a quite insightful idea. Anyway, so back in antiquity, there was this notion that the world might be made of discrete things, put together in different ways. The question of whether that meant that space itself was discrete, I don't think was really addressed. I think it was more the stuff that we have, what is it made of? There was sort of a different tradition from people like Heraclitus that was kind of the everything flows tradition. Everything is really a continuous thing, and there's things are made out of those continuous objects. Then there were things like Zeno's paradox, which was sort of a confusing intermediate case about asking, if you say, well, there's Achilles and the tortoise, and they're each going this amount at this time, and so on, without an understanding of continuous mathematics, that came in much later, like in the 1600s and so on, it wasn't really easy to kind of unravel that kind of paradox, because that kind of paradox is asking, you subdivide, and if you say, well, you can keep subdividing forever, which is kind of the conceit of continuous mathematics and the continuous view of space, then you can kind of resolve the paradox that way. But if it seems like you're talking about subdivisions and you can just make a kind of concrete subdivision at a particular level, then it still seems quite paradoxical. So I think that was the story in antiquity. And it wasn't like people were sort of imagining space as a thing you could talk about in and of itself. Euclid, for example, in setting up geometry and writing down kind of the way to think about geometry, his very first postulate or definition, I guess, is a point is that which has no part. In other words, he's assuming that there is a notion of an infinitesimal geometrical point. And then he goes on to say a line is that which has no breadth. So it's again, these ideas which implicitly assume kind of a continuity of space are present in Euclid. What did Euclid think he was doing? He thought he was trying to sort of clean up what you could deduce in sort of practical terms by just drawing diagrams on pieces of slate or, having rods representing different sides of a triangle and so on. He thought he was just trying to make a more perfect system that ultimately represented what is observed in the physical world. He wanted to sort of turn into philosophy, in a sense, that which before had been a thing that you just did with measuring rods and so on. And that, I think, is, and so, for example, for him, the idea that two parallel lines can never intersect was, I think, quite obvious. That was a postulate he had, his so-called fifth postulate. That was just a thing where, from everyday experience, parallel lines just don't intersect. Now, it took until the 1800s for people to say, wait a minute, you could imagine a version of space where parallel lines can intersect, as they would do on curved spaces and so on. And then it took from the early 1800s, 1830s and so on, up until Einstein in 1915 to start talking about, well, maybe physical space is actually curved in that way. But so the idea for Euclid was he's kind of reproducing sort of in an idealized form what his common experience says about ordinary physical space. And for him, it's sort of obvious that parallel lines can't cross. For him, it's obvious that there can be an infinitesimally small point, that lines can have no breadth, and so on. So for Euclid, he's kind of implicitly assuming there's a continuity of space. For the only sort of chink in that armor is the story of the Epicureans from Democritus on, who thought of at least the stuff in the world as being made of discrete atoms. I think they still imagined that it was kind of their version of it that was used was atoms and the void. So the void is that which is not part of the atoms, so to speak. And I think they kind of imagined that you could sort of put the atoms anywhere you wanted, and sort of the void was everything, which included when there wasn't stuff there. They didn't really understand gases and things like that. They certainly didn't understand vacuums. That came much later. But so for them, it was just like there's places where there's stuff and there's places where there doesn't seem to be stuff. And so all the stuff is represented as different combinations of these discrete atoms, and the places where there isn't stuff is the void. Okay, so we then go much later. I guess Descartes in the mid 1600s, is that right? Maybe a little earlier than that, I think. Early to mid 1600s. And Descartes kind of wanted to have sort of a model for everything in the world, and thought about this idea of vortices, that everything was kind of made up of these different vortices. That was kind of his version of the atoms. And I think he had some notion that was a little bit like, not quite discrete space, because people still imagined that Euclid was the kind of gold standard, that Euclid was the idealized representation of everything about geometry and space and so on. So when Newton, 1687, got to write his Principia Mathematica, mathematical principles of natural philosophy, he was modeling that on Euclid. And for him, the idea that he had the sort of base of the geometrical structure of space, and then he was discussing how things in space would be attracted by the law of gravity or whatever else. So at that point, kind of the notion of discrete of space was just this Euclidean thing that was a background to the things he were doing. I think, as I say, Descartes had a slightly different and perhaps a bit wacky view about sort of everything is made of vortices and so on. I think, let's think. After that, kind of the next sort of thinking about the nature of space came with relativity, 1905, and the idea that there could be sort of different, that space wasn't just that Euclidean thing that just was what it was, that there was more kind of freedom and dynamics in space. And for Einstein, that was the idea that lengths and times and so on, that lengths in particular were things that depended on the observer. There's the Lorentz contraction. If you're going faster, things seem foreshortened and so on. And that the idea that space was sort of a fungible thing, not kind of this fixed Euclidean background. So then in 1915, with general relativity, came the idea that you can think of space as being curved, that and that in fact in physical space, you have those two laser beams going off in parallel, making lines. If there's gravity in the middle, those laser beams can be attracted together, and you can represent that attraction by saying that the space in which the lasers are, the laser beams are carving out kind of shortest paths, that space is curved, and that's kind of an account of what the force of gravity corresponds to. So the idea that sort of space then was this dynamic thing whose structure depended on the presence of matter was a thing that sort of came in 1915. So around the same time, I mean, it was in the 1800s, that people were still asking the question, is matter discrete or continuous? So 1600s, Newton had talked about the possibility of corpuscles and had various even models for what gases might be like. The Bernoullis had models for gases in which they were made of discrete sort of atom-like corpuscles. And I mean, Newton famously had his universal law of gravity, the inverse square law. He also had a hypothesis for the sort of law of interaction between things in a gas that he imagined might be atoms. He had a fifth power law that doesn't turn out to be right. But that was, at that time, that was being discussed. But it was still something where people weren't at all sure that the atomic theory of matter made any sense. And famously, Ludwig Boltzmann spent a lot of his life thinking about the atomic theory of matter. And by the end of the 1800s, sort of given up. Nobody seemed to believe in it. They didn't even believe in it. They didn't believe in the kinetic theory of gases. They just didn't believe in the discreteness of matter. And he sort of famously said, he's writing down a book on the kinetic theory of gases based on discrete atoms and molecules. He says, I'm writing this down, even though nobody believes it right now, and one man cannot stand against the tide of history, he said. But I'm writing it down, he said, so that, in the future, when this is rediscovered, it will be brought out again and people will find what we've done now useful. Actually, it was not very long at all and it was being rediscovered. And that was in large part due to Einstein pushing kind of discrete things all over the place. So in studying Brownian motion in 1905, it had been studied a bit earlier by Smolchowski and others. This idea that Brownian motion, when you look under a microscope, you see little pollen grains being kicked around, that was due to actual impacts of molecules on those little pollen grains. And so by 1900, there was a sort of serious view that matter might be discrete. I mean, there'd been evidence of that from all kinds of things Boltzmann had done and accounting for properties of gases. There'd been evidence from chemistry, from people like Dalton, noticing that there were these sort of integer relationships. It's water is 2 hydrogens and 1 oxygen. It's not, 2.7 amounts of hydrogen and 0.82 amounts of oxygen. It's these discrete numbers suggesting that there are discrete atom-like things that make up these chemical compounds. So, and then in 1905, the idea of photons as discrete particles of light sort of really got pushed. I mean, Planck in 1900 had kind of leveraged ideas from Boltzmann to kind of account for blackbody radiation using implicitly the idea of discrete corpuscles, particles of light. But Planck didn't really believe in that. He just thought it was sort of a mathematical trick. It took him a decade or more to really believe in that. Einstein was the young activist, so to speak, who first believed in sort of the true discreteness of light as photons and so on. So by 1905, a lot of discrete models of things, matter, light, and so on. And then as quantum mechanics started to develop by the 1910s with people like Bohr and Rutherford and so on, and then by the 1920s with Schrödinger and Heisenberg and so on, the idea that sort of everything was fundamentally discrete got to be really a thing. So at that time, although the history is really obscure, and I really need to go really track it all down sometime, because a lot of it is really not published, because people sort of tried to say, well, we know matter is discrete, we know light is discrete. So what about space? Maybe space is like an egg crate, a big kind of discrete collection of cells. I think Heisenberg had that idea. I think. I don't know. He didn't publish that idea, but I've heard from people that he had that idea. Now, there were other things that were sort of questions about discreteness of space. Like, for example, one of the big questions was, it was known that accelerated electric charges radiate energy. That's what allows you, as you move the sort of electric electrons back and forth in an antenna, you're accelerating, decelerating, and so on. That produces an electromagnetic wave. And so one question was, when you have an electron in an atom, it's really true, as became clear with Rutherford and so on around 1910, that the atom has a nucleus, the electrons are sort of going around the nucleus. People like Bohr had sort of had to wonder, why is it the case that the electron, as it's kind of orbiting around the nucleus, doesn't do the thing that electrons, which are accelerated, because anything that's kept in an orbit is being accelerated, otherwise it would just go in a straight line. Why is that electron not radiating energy and spiraling into the nucleus? Because it loses energy. Why does that happen? And one of the ideas of that would be, oh, because there's sort of discreteness to space, and it can't just sort of spiral in, it's got to be in one place. That was sort of one version of this. So kind of the notion of discrete space was something that was definitely in the air, and people kind of imagined everything's going to turn out to be discrete. I think Heisenberg was one of the people who pushed this further the most. I think it was around the early 1930s, where he just sort of gave up. He said, I can't make this consistent relativity. If you have a bunch of sort of egg crates in space and you say, well, what do those look like to an observer who's traveling at 0.9 of the speed of light? Well, it doesn't seem to work. It doesn't seem like there can be a thing that is a discrete kind of array of things in space. That just doesn't seem to be a thing that's consistent with the ideas of relativity. So Heisenberg at that point said, well, forget about doing this. Let's just think about kind of interactions between particles as being things where there's an incoming state and there's an outgoing state, and something happens in the middle. And we're just going to describe that by this thing we call the S matrix, that is just this mathematical object that represents the transformation from incoming configurations of particles to outgoing configurations of particles. And that's what led to S matrix theory, which was one of the sort of drivers of modern particle physics and string theory and so on. But that came out of sort of Heisenberg's frustration, apparently, with the idea that he couldn't figure out what was really going on inside there, and because he couldn't figure out sort of what the structure of space might be. So, well, then kind of the notion of should you think of space as being discrete or not didn't really come up for a very long time. And in physics, people just assumed space is continuous. General relativity had been invented in 1915. It didn't really get seriously worked on until the 1950s and 1960s. There was a long period of time when it was just kind of like, oh yeah, it's a thing, but it wasn't really studied. The nature of black holes was not understood. It wasn't really understood whether they were a real thing, whether they were a pathology in the theory, and so on. But when general relativity kind of came back to being studied, it was like, of course, it's a continuous background of space. And when it came to particle physics, it's of course space satisfies relativistic invariance, and that means that, and it has Lorentz transformations which can be at any velocity. So similarly, you can say, well, we can also take space and we can make rotations. And the idea is, it's not just you can make a rotation through this discrete set of angles, but you can make any rotation in space. And the generalization that is Lorentz transformations, where you're making rotations in space-time. And sort of the implicit assumption throughout particle physics was space is continuous. You can, just like you can describe possible rotations in space by the rotation group, you can describe possible sort of transformations in space-time by the Poincare group. It's a continuous thing. Don't even think about anything else. So what happened beyond that? Well, starting in the 1940s, people started thinking, how will we take things which are usually described as continuous, like fluids, and kind of simulate them, solve the equations for them on computers? And that led to the idea of, well, let's make a mesh where instead of saying what the velocity of the fluid is at every point that you would mathematically define, v of x, y, z or something, for all x, y, and z, you would just take a discrete mesh of points and say, we know the velocity is this at this point and that at the neighboring point, and so on. And even, for example, von Neumann, around 1950, started thinking about weather forecasting by computer. I mean, von Neumann was often a good ideas, but not completely thought through. This was one of those cases, I think. It was like, it's going to be easy to do weather forecasting. He and a person called Charney were kind of off and doing that. And it was like, it's going to be easy. Well, 70 years later, we can more or less do few-day weather forecasting by solving those equations, by discretizing kind of the space and for a computer. But so that idea that you might discretize things for the sake of putting them on a computer was a thing that had come in by the 1950s, 1960s, and so on. But it was viewed as well, that's what you have to do to take real space that's continuous and stick it on a computer. There were sort of a long stream of what one might say, I guess, amateur scientists. I view myself as an amateur scientist in some ways as well, but scientists, I would say, who were probably much further from the mainstream than I am, in the sense that, I mean, I have the feature that I kind of learned and did traditional science before I started doing things which were beyond traditional science. The folks who were kind of the discrete space crowd mostly were people who did not know the kind of traditional canon of general relativity and things like this, and would just say, hey, wait a minute, let's do something different, without kind of knowing what there already was. So a couple of people along those lines, one, a chap called Konrad Zuse, who was a German computer technology pioneer, who I never met. I exchanged letters with him. It's somewhat confused in the historical record because he had started talking about calculating space. And I think he was just thinking about finite difference, kind of the idea that you could have you could make space discrete for the purposes of computation. Some of that is kind of shrouded in confusion because during World War II, Zuse had made apparently a mechanical computer, and with help, it seems, from the German military, and it was particularly the German Air Force. What it was exactly used for in the war, I don't know. It's not publicly known to my knowledge. To what extent the idea of, we're going to solve the equations of fluid mechanics, and we're going to do that by discretizing them and put them on a computer, and then that turns into what he called calculating space. And then it's like, well, maybe that's how the whole universe works, because, well, it's at that point he was running a small computer company, and it's like, let's sell computers and so on. I don't know to what extent all those pieces were mixed together. It is true that in England, there was a chap called Richard Southwell, I think, who was responsible for the design of the wings of the Spitfire fighter. And he had used kind of finite element methods, discretizing kind of the fluid, the velocity of the fluid in discrete elements. And he had human computers, actual humans doing computations, but the idea of kind of discretizing space for the purpose of calculation was apparently important in the design of the Spitfire fighter, which has kind of notable different shaped wings than previous things had had. So I don't know to what extent. I mean, I do know that, or I've heard that it's been hard to get the information, but I've heard that Konrad Zuse was connected to the Luftwaffe in Germany, and so it would stand to reason that there was some similar kinds of thinking going on there about calculating sort of fluid motions there. So that was sort of one branch. And as I say, the historical record is a bit confused because by the 1980s, my own work on cellular automata existed, and Konrad Zuse had sort of corresponded with me and started talking about cellular automata, but that was presumably very different from what he was talking about in the 1950s with his calculating space, but not completely clear. That's one branch. Another chap who I knew well was a person called Ed Fredkin. I wrote a very long and elaborate obituary for him a couple of years ago. He kind of got the idea. He was really into computers. He knew computers. He didn't know physics. He was interested in physics, but he didn't really know the traditional canon of physics. And so for him, it's like, I build things with computers. I engineer the software world with computers. Let me engineer the physical world of the universe. And so practically to his dying day, he would routinely tell me, I've discovered the electron, so to speak, and things like that, in thinking about discrete cellular automata with particular phenomena and sort of identifying analogies between those and what happens in the physical world. But his notion that sort of discrete space can be made, as I think Heisenberg had imagined also, as sort of this discrete lattice of points where there's sort of a thing moves from one lattice point to another. It's first of all a challenge to deal with rotational invariance, but you can get things which are approximately rotationally invariant. I mean, Ed Fredkin had a thing that he, I think, called his SALT model that he said was rotationally invariant in the sense it was on a discrete square grid. But he says, well, if you make a big enough version of it, it will be circularly symmetric. I actually worked that out in this obituary, and it isn't true. It's approximately circularly symmetric, but not exactly. Now, of course, we don't know that the physical world is exactly circularly symmetric, but it's certainly to a better approximation than this would lead to, because even in the large scale limit where the lattice is very, very big, Ed's version of this still isn't circularly symmetric. So, but in any case, there's some that was sort of a strand which I must say that I had found very frustrating, because I was studying cellular automata, discrete kind of versions of space, but I viewed them as being not the way the physical world is, but an approximation to the way the physical world is, in the same way that endless other models of the world are. I mean, one doesn't imagine that, in the equations of fluid mechanics, that the fluid is solving that equation. It's merely the equation represents what happens in the fluid, and then we get to separately go off and solve the equation. So in the early 80s, I was interacting with folks like Ed Fredkin and others who were, really like, we can make everything out of cellular automata. And I was like, no, one can't. It's obviously not consistent with relativity, same issue that Heisenberg had encountered. It just, space, I reasoned, was not as kind of rigid as just an array of cells. So I just kind of was very put off this idea, and I was sort of fighting off this idea because people were like, oh, are cellular automata really supposed to be a model of the universe? Well, no, they're not. They are like differential equations, like other kinds of things. They're one of the kind of collection of tools that you can use to model things. If you're modeling the pigmentation pattern on a mollusk shell, you're not modeling the underlying structure of space. You're making an approximation to maybe the cellular structure of the mollusk or something, but you're not, so it doesn't matter that you say that it's a discrete grid of cells, but you're not modeling the underlying structure of space. So for me, that was about 1990 that I started thinking about kind of networks as kind of a potential model for what's underneath space and time, a thing that is not like a rigid grid where space has already been defined, but something where it's kind of flexible enough that you could have that you could that you can kind of make something that emerges to be like space from something that's discrete underneath. And it wasn't until 2019, well, actually, by the mid 1990s, I understood how one would get relativity and general relativity from these discrete network systems, and why the sort of the issues about sort of having to pre-build the structure of space were not issues anymore. But there was some, and so then by 2019, really got serious with our physics project, and we were able to figure out a lot more about sort of the derivation of the Einstein equations for the structure of space-time and how that can all emerge from underlying discrete space. Okay, there are other strands. There are, well, let's see, a couple of other strands. One associated with John Wheeler, one associated with Roger Penrose, and I suppose one associated with quantum gravity in general. So let me see if I can untangle these strands. So I think John Wheeler, I'm trying to remember what the origin of his interest in discrete space was. But he was eventually interested in, he had this whole sort of program of it from bit, which was kind of the idea that information is the fundamental thing in the universe. I agree with that.